It all starts with the spinning hydrogen nucleus. Biological tissues contain water, and hydrogen, of course, is part of that. Because the hydrogen nucleus has a positive charge, being a proton, when it spins, it generates a magnetic field. So it has a magnetic dipole moment, a north and south pole. Now in the scanner, the basic magnetic field, we call it B0, runs along the z-axis, the same direction the patient is lying. Consequently, the spins on the tissue's protons are now at a frequency that is precessing, like a gyroscope, directly related to the strength of the magnetic field B0. I think it's worth showing what precession really looks like using the example of a top. What you're seeing is that the process of precession means that there's a fixed angle that the top maintains with the Earth's gravitational field, and the motion is one of precession when it goes round at this fixed angle, spinning at its resonant frequency. In the case of magnetic resonance, what's precessing is the magnetic field of the hydrogen in the presence of an externally applied magnetic field. In this case, we call it B0. The magnetic fields of many of these nuclei, and there are trillions in the body, add together to form a macroscopic magnetization, which we call vector M, and that is aligned with the field direction, aligned, in other words, with B0. To excite the signal from these protons, we use the RF coil in the scanner to send in a pulse. Remember that, until this happens, M and B0 are aligned in the same z-axis in which the patient is lying. But the RF pulse generates a weak oscillating magnetic field, call it B1, which can only tip M out of alignment if it oscillates at the same frequency as the protons. We call this resonance. In this case, it tips it 90 degrees into the XY plane. Once in the XY plane, the macroscopic magnetization M rotates around the B0 direction, so it starts rotating in this plane, and this rotation causes an oscillating magnetic field which is picked up in the receiver coil, which is typically a loop of wire that surrounds the object. After the excitation of the 90-degree pulse, the protons begin to relax and so to realign with the B0 field in the z-axis. They manage this relaxation by exchanging their spin energy with the surroundings, what we call the lattice. The exponential curve shown in this graph is known as T1 relaxation, a measurement of the time it takes for the protons to get less and less excited and return to equilibrium. At the same time, there's another completely independent process of proton relaxation happening. Instead of giving up their excess energy to the lattice, the protons also relax by exchanging magnetic energy with each other. This exponential decay we measure in the XY plane. The exponential decay rate is characterized by the T2 relaxation time, which is typically of the order of tens of milliseconds, and this also varies between tissues. So there we have it, T1 and T2, measurements that can mark the difference between biological tissues. But how do we progress to imaging? Magnetic resonance imaging. Now we can explore the process of acquiring an image.